Okay, let's get started with a simple model that characterizes diffusion in a square region. To start off this model, we'll import the physics interface transport of diluted species, and we'll uncheck the convection box here that will be checked when you first start. And we'll just make the geometry this 1 meter by 1 meter square region that's just will work fine for a default geometry. The setup, all of this stuff, well, we'll get to the definitions in a second, but let's take a look at the setup of the physics. The diffusion is just going to use the default diffusion coefficient of 10 to the minus 9. These are default values, the no flux boundary, and the initial values will be that the concentration starts out at 0 everywhere in the square. The boundary conditions are that the concentration on this side is 0, and on this side the concentration is specified as 1. Now, the mesh is a little bit finer than the default. I'm using just an extra fine mesh here. And the duration of the simulation is 10 to the 8th seconds. So we run this and it solves very quickly. And let's take a look at the results. So this is the concentration distribution after 3 times 10 to the 7th seconds. And if we go out to 10 to the 8th seconds, it spreads out even further, coming pretty close to this edge. So we can take a look at how this distribution evolves with time. We start off here, and the this font really just moves in a very smooth way outward from the edge. This is essentially functioning like a half space, where this would be a surface, and this is essentially an infinite region going in this direction. At least it's functioning as a half space up to this point, where we don't really have any interaction between the diffused mass and this far field, or this boundary here. So we can plot this along an axis that goes parallel to the x-axis, and the concentration distributions look something like this at these different times. And you can see by 3 to the 7th, we really haven't interacted with the boundary in any appreciable way. So what I want to do is to plot the mass that has diffused into this region. So pretty clearly right at the beginning we have 0 mass that's diffused in, but then with time we get more mass. And basically what we need to do is integrate this mass distribution that we see here. So the way I'm going to do that is to go up here to definitions, and I use model couplings, and then I can insert one of these guys, and I'll use just the integration function right there. So I put that in, and I already did it. Put it in right there, and I can integrate over several different regions. And what I want to do in this case is integrate over the domain, and I select this domain. This will do an integral over this, in this case, this area. And when I go down here to the plotting in the post-processing, if I select global in this 1D plot group, I get an interface that looks like this. And in this expression, I type region, which is the name of the function that I set up here that does this, solves this integral. I write region, and then in parentheses I give it the integrand. And so this thing here will integrate the concentration over the area, and that will give us the mass per unit thickness within the region. And so I plot this as a function of time, and here's the result. So this is behaving like, I guess this looks like square root of time, which is what we would expect.